morning. So, previously we talked about this particular system here, that one side is NH3 and the other side is N4, okay? And different times we have to take care of different properties of metal ion and the compound itself. So, today I will show you other reversible systems. Anyway, before I show you other reversible systems, some very important points about these systems. So, in this system what happens is, my metal ion was here, it will go from here to here. I can write a cartoon also. I am not saying that it is against gravity, not like that. It is like sulfur, nitrogen, 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 and it go to sulfur, 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 nitrogen. Okay. So, the metal ion goes from here to here. So, this kind of systems are they are like live. So, you give this some energy. In this present case, I am reducing it copper 2 to copper 1 and it is going from left to right. Then again it is air oxidation, it will come from right to left. So, it is a fun, not only fun, this can be very important elements of making different molecular devices, molecular machines, and that depends upon your ingenuity, your how you conceive some molecular machines like that. Okay. So, it goes from one end to the other. Now, the question that comes to our mind, how long it takes to go from one end to the other? Well, when we first see, unfortunately, it takes about 18 hours for this, 18 hours. For this system where we have ortho, see that ortho substituted. So, this orthocryptand, let us call it orthocryptand. In case of this orthocryptand, when I reduce it, it goes from here to here in 18 hours completely. And how we monitor that? We monitor that through fluorescence. So, when it go from here to here, then what will happen? PET will be on, and because PET will be on because the metal ion goes from here to here. So, it cannot engage this nitrogen lone pair. So, PET will be on, and if PET is on, PET will be on, there will be no fluorescence. But when metal is here, then PET is off. So, therefore, it will give a strong fluorescence. So, in this particular case, fluorescence is actually telling us what is happening in this microscopic world, that metal goes from here to here. Unfortunately, it takes 18 hours and we monitor it, that slowly it comes to 0. In this case, what happens in this case? Difference between this system and this system is that they are similar. However, here this aromatic group is meta substituted. Okay. Meta, because it is meta substituted, it is rigid. So, this cavity is rigid. In this case cavity collapses little bit, and it can rotate and it can but in this case cavity is quite rigid. Okay. So, let me write more rigid cavity, more rigid cavity. So, more rigid cavity in this case. So, therefore, it takes less time. How much less? About 15 hours, no good also. From going from this part all the way to this part and coming back. 18 hours. So, with 18 hours you cannot do anything. So, then what happened? This is a very important, I made a blunder here, I made a blunder, let me change that. Yeah, let me change that here. What happens here is, okay, this space, I am writing this space, I do not have space or time, hopefully you will understand. What is this? This is equal to this, okay, is para substituted, and there are two phenyl groups. So, there are two phenyl groups. What is the difference between this and this, or this or this? This very important difference. In this case, this is the hydrophilic part or metal binding site. This copper 2 binds here, copper 1 binds here, but in the intervening space, in between, we have two phenyl. In this case, we had only one phenyl, but here we have two phenyl. So, here we have a longer hydrophobic space, is a much longer hydrophobic space compared to here or here. Because of hydrophobic space is longer, what can happen? So, this is one more important information. Metal ion, if you put in a hydrophobic space a metal ion, then it will run away from it much faster. So, a metal ion putting here, okay, putting here copper 2, putting here, copper 2 will go here, will come here. It takes how many times? From 18 hours or 15 hours, we come to minutes. Within couple of minutes, it does like this. And why it does so? Because two reasons. This space is kind of rigid. This is a rigid hydrophobic spacer. So, this is a rigid. So, the ball comes, and ball comes in 2 minutes, and their ball comes in 18 hours. So, 18 hours is not good, but 2 minutes is much better. So, we are not done here yet. So, if we do, you might tempted to think, if we do something like this, well, synthesis are not very easy, and this was one of my last work at IIT Kanpur before I retired. So, I am now home, I cannot do anything, but one of you can take up and do this. If I put this, okay, if I put this here, then I bet it will be in seconds, okay, less than a minute. So, we want that, we want this movement this way, that way, this way, that way. That means, when it is on the on this side, then PET is off and we will see lot of fluorescence, and when it comes here, there is no fluorescence. That means, every second is lighting up, switching off, off, on, off, and not like here, on, then after 18 hours off, not that. Or in this case, it will be in minutes, several minutes, on, slowly off. So, you cannot think of any other device with these things, but if we have even increasing hydrophobic space, then it will be much faster. From 15 hours, we could come to minutes by only 2. So, if we put 3, difficult to synthesize. Okay. So, there have to be Suzuki coupling and so on and so forth, and not very trivial, non-trivial synthesis. If you can make it, then metal will go here and come here immediately in few seconds, couple of seconds maybe. That means, when it comes here, I see light, bulb, says it is like a bulb is on because fluorescence is on. When it comes here, off. So, these can be used in fabrication of molecular machines. All right. So, that is an important. So, there are many aspects of these supramolecular systems. That is a coordination tendency of the metal ion, its redox availability, okay, and this hydrophobic spacer. So, many things goes like that. It is not like you just make A plus B, you get something and get the product. So, you have to think, you have to design. So, I encourage all of you to design. When you go back, you design, then you can make some interesting systems. Okay. We have made only up to this, and then I do not have any lab, I cannot do anything. All right. So, this is about this system. So, not only cryptan, but macrocycles can also be used on and off, okay. Fluorescence on and off. Here of course, the metal ion is not, metal ion is strictly held here, nickel. I told you that this is called cyclam, 14 member tetra-aza compound. This cyclam likes to bind nickel 2 plus very well, because they are matching, okay. Size and shape are matching with nickel 2. So, when nickel is 2, then this one is up out here, okay, when nickel is 2. Now, so if we excite it, it gives fluorescence. This is a fluorophore. It is a high energy, but it still is a fluorophore. This is also a fluorophore. So, how do they give reversibility of fluorescence? Here, if I put nickel 2 plus, I get fluorescence, because this is the system. If I make nickel 3 plus, I can oxidize it electrochemically. If I make nickel 3 plus, it is not going to run away from this pocket. Why? Because this pocket is made for nickel. It makes a very strong, very stable macrocyclic complex with nickel 2. And if nickel 3 plus, that means charge is from 2 to 3. So, it likes to bind this oxygen. Oxygen will come here and bind. And when oxygen comes here to bind, it is a paramagnetic, so it will be quenching. So, no fluorescence. So, that means when there is nickel 2, I see fluorescence on, I oxidize it by some means electrochemically, okay. You can oxidize it many ways. So, electrochemically I oxidize it, and then I see interaction. I do not see interaction between this and this is the mechanism. So, when it come oxygen to nickel 3 plus, then because of this interaction direct, you remember that metal fluorophore interaction, communication, metal receptor interaction. Metal receptor interaction should be good, metal fluorophore communication should be bad, then only we see fluorescence. In this case, metal fluorophore communication is good when nickel is 3 plus, here as well as here. So, these two are so reversible fluorescence because of these things. Another important, I am just drawing, I did not have time to everything to draw these things. Let me draw it now. I will waste some time, but it is okay. What to do? So, this has been designed, this compound. Okay? N NH NH. Then 110 2,2 dash bipyridyl. This is 2,2 dash bipyridyl. Okay. So, this 2,2 dash bipyridyl, yeah, I got this, and similar is the case here. By mistake, I keep on now. I am trying to hurry it up and making mistake. Let me put this way. Okay. So, this is a compound. What you can see? Here is a binding site, here is a binding site, here is a binding site, amide. Amide actually NH, NH. These are amide. Amide, or some people say amide. Okay, amide. So, this is 2,2 dash bipyridyl. 2,2 dash bipyridyl makes a very good complex, stable complex with nickel 2. Here now I am not talking about oxidation of this. Here ligand has some magic for us. So, when nickel 2 is bound here, okay, here is one coumarin derivative. Let me write coumarin derivative. Unfortunately, I have to spend this kind of time for drawing, but sometimes it may be okay. 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 This is a coumarin derivative and it is a carboxylate. Okay. This coumarin derivative is excited at 430 nanometer. It is written, so I am writing 430 nanometer. If you excite it, it will give you strong fluorescence at 471 nanometer. This is the property of this particular coumarin derivative, coumarin, all right. So, this coumarin derivative, if you excite it at 430, you will see 471 nanometer strong fluorescence. And so, when nickel 2 is here, nickel 2 is bound through coordination here, 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 here. That time if you give this coumarin derivative, it binds through carboxylate, okay? It binds through carboxylate. Because it is a square planar, so from top or from bottom something can bind. So, let us see, let us consider only from top. So, from top this carboxylate will bind to nickel. So, I am writing this nickel coordination, okay. Nickel will bind a coumarin derivative here, and since it is directly bound to nickel 2 plus, and so therefore, it is a transition metal and it will quench fluorescence very effectively. So, if I now excite it at 430 nanometer, there will be no fluorescence, because this is directly bonded to nickel 2 here. Now, this is pH around 7. So, here my variation is pH. At pH 11, strongly basic, pH 11. At pH 11, strongly basic, what happens? These amide protons are acidic in nature, and at pH 11, both these protons will be lost. At pH 11, strong base, and this amide is acidic in nature. So, acid base reaction will work and these protons will vanish from here, whole thing vanish, and it will become negative and negative. So, that is called deprotonated amide. Deprotonated amide makes a strong bond, but protonated amide or simply amide does not make a strong coordination. That is why nickel was initially here at pH 7, but as soon as I increase the pH, the hydrogens are gone and we have deprotonated amide. Deprotonated amide will strongly bind. So, nickel now goes from here to here, it will bind, strongly bind, okay. So, here is nothing, here is nothing, here is nothing, and because all the nickel 2 plus is bound now here, and because it is a very strongly sigma donor, strong sigma donor, let me write deprotonated amide is very strong, especially aliphatic, very strong sigma donor. That means, it can donate electron density very strongly to nickel. Then what happens? Nickel is getting two strong donors from this side and one from this side. So, therefore, what will happen? It will not have a tendency to bind carboxylate. So, in this case, at this point, there is no sigma donor, no sigma, strong sigma donor and all that. So, nickel when it was here, it could bind coumarin derivative, but when nickel 2 is here, because of this deprotonated amide is very strong sigma donor, it will not bind coumarin. So, coumarin will remain as such free. Because of that, what will happen? When now we excite it at 430 nanometer, we see very strong emission, fluorescence emission. So, that means, we take this compound and put nickel as well as coumarin. Now, we excite the coumarin at 430 nanometer, we do not see any at pH 7, we do not see any fluorescence, it quenched. Now, we increase the pH to around 11, very strong basic, and then we see very strong fluorescence. So, that means with pH change I can get reversibility of fluorescence. All right. So, therefore, what I have talked to you about this previous day and today are the reversibility of fluorescence. Okay. Reversibility of fluorescence, only few methods I talked to you about. That does not mean it is exhaustive, there is nothing beyond this, everything depends upon our imagination. You apply your imagination, you make your own design and you have reversible fluorescence. Eventually that can be very useful in many we have in many situations. Yesterday we showed you previous class, I showed you how mercury specific system that can detect mercury up to 3 ppb parts per billion, okay, that can detect, and that is very useful in treating mercury poisoning. See, in Japan there is a place called Minamata Bay, okay, Minamata Bay, and from Minamata Bay there is an industrial hub. So, we must tell stories also to remember these things. So, Minamata Bay, I will now take stories only. In Minamata Bay, what happened? There is a Kawasaki motorcycle and there are other industries. So, they were effluent from industry, like effluent in the industry, and in that effluent there was mercury. There was small amount of mercury going into sea, and fish will eat those, and when fish eat, then human beings will catch those fish and then human beings consume that. So, from industry mercury is coming to human being, and mercury is one of the most poisonous elements. It affects our nervous system. So, there was a disease called itai. Itai in Japanese means paining, lots of pain, and the people will die. So, in those situations, that means why people could not understand. So, if we have this mercury detecting compound, then immediately you give it to them and you see through confocal microscopy that spots are there. That means mercury is present in our body, that is why I am having this pain and I am dying. So, they can immediately treat me for mercury, because the doctor must know what is my problem. So, these are the very important uses of fluorescence spectroscopy, okay, apart from material science like I told you. All right. So, I thank you in this class, thank you very much. So, next time I am going to discuss another very important aspect. Thank you.